Let us see this problem. We are given a binary search tree where two nodes are swapped. We need to correct the BST. So the given tree is almost binary search tree with two nodes being incorrect. We need to just swap back these nodes and correct the BST. Let's see this example. In this example, if I swap 60 and 8, I will get the correct BST. So my output should be 8 and 60. You can notice after swapping these two, all BST properties everywhere are satisfied. Everything in left of 20 is small, everything in left of 8 is small, everything on right is greater. Same here. If you see this BST, I again have two nodes which are swapped with each other, and if you swap these two nodes back, you get the BST. For example, if you simply swap 20 and 60, you will get the correct BST. So the two nodes which were swapped earlier in the BST are 20 and 60. So you are given such a tree, you need to find the two nodes which are supposed to be swapped. Then you need to swap these two nodes and correct the BST. Now please pause this video and think of an approach to solve this problem. Let me give you a hint to solve this problem so that you can again pause and try. The idea is based on the last solution that we discussed for checking for BST. In that problem, in the last solution, for every node, we were checking whether this node is greater than previous or not. Right? So we were basically doing an order traversal. We were maintaining the previous and then we were figuring out whether the given tree is BST or not. Something similar we need to do here. So you can again pause the video now and try this yourself. So the idea is based on in-order traversal here again, we do an in-order traversal of given tree, and a simple solution can be store this in-order traversal in an array and then find the two nodes in the array, swapping which will cause the array sorted. So I have in-order traversal of this tree in this array. This is 4, 60, 10, 20, 8, 80 and 100. That's what we have in this first array. And in the second example, the in-order traversal will be 4, 8, 10, 60, 20, 80 and 100. I've taken two examples. I am explaining them again because there are two cases that arise when we solve this problem. The two cases are if the swapped nodes are adjacent in the array or in order traversal, like this case. 20 and 60 are adjacent and they need to be swapped to fix the array. If you see this array, they are not adjacent, right? The first node is 60 and second node is 8. So if you traverse this array and find out violations against sorting, which elements are not following the sorting order, you will first find the violation here, then you will find a violation here, right? So other nodes are following the order. For example, 60 is greater than 4, 20 is greater than 10, 80 is greater than 8, 100 is greater than 80. These are the two nodes which are not following, 8 and 10, right? They are not greater than their previous elements. If you see this array, in this array there is only one violation. Everything is following the order except 20. 20 is smaller than previous nodes. Everywhere else you have no violation. So there are two cases. When you traverse through the in-order traversal, you will find two cases. In one case there will be two violations. In other case there will be one violation. So please pause this video now and try to solve this problem for an input array. You may reduce the problem as you have an array. You need to fix the array by finding the two elements of this array which are swapped. Once you have solved for the array, it's very easy to solve it for a tree without using auxiliary array. Here I have written a solution for an array. I have initialized first and second as nil. Nil may be some special values which may not be present in the array. I have initialized previous as minus infinite. I traverse through the whole array. Every moment I check if array I is smaller than previous. Because if array I is smaller than previous, that's where we have a violation. If there is a violation, then we check if first is nil. If first is nil, then we make first as previous. And we always make second as current node, right? Array I. Second is always set as current node. And after every iteration, whether there is a violation or not, we update the previous. So we are basically checking whether array is increasing order or not. And whenever we are seeing a violation, we are updating first and second. These first and second are our resultant elements which are supposed to be swapped after this traversal. If they remain nil, it means there was no swapping required. Let's understand this idea with these two example cases. One case when two nodes to be swapped are not adjacent, and the other case when they are adjacent. In one case, what happens is when you traverse through this array, you see the first violation at this moment. At this moment, you see that this is violating. This is smaller than the previous one. So in this case, what do? You update the first as the previous one and you update the second as current node. Now you come to 20, you come to 8, and when you come to 8, you see there is a violation. So this time you need to consider the current node of the violation. In the previous case, your output was previous of the violation, right? So you see a violation, what you do? You again check whether the first is set or not. First is this time set. First is already set to 60, right? So you do not update the first. You only update the second as 8. So once you have done the traversal, your first remains here and your second remains here, and you have the correct first and second. Now if you see this example, when you traverse through this array, you see your violation at this point. This is where you see first violation. You set the first as this, second as this, right? You traverse through the whole array, and after traversal, you need to swap first and second. So the idea is this: if we see first as nil, then we update first, and we always update second, right? So this way we handle both the cases. We can extend the array solution for a tree also. We can have some references, first and second and previous, and these three references are shared by all the function calls. You can make them shared by using global in C++ or a class variable in Java. In C++, you can also pass reference to a pointer or pointer to a pointer. So you do an in-order traversal, you initialize first and second as null. While doing the traversal, if you find a violation and if first is null, you set the first as previous, and in every violation, you set the second as current, right? And you follow the same in-order traversal that we discussed in Fix BST approach. And at the end, after the traversal is complete, our first and second will be appropriately set. And at the end, we simply need to swap first and second. Here are C++ and Java implementations of the approach. Please note one thing about these codes. They do not swap the nodes which are violating the BST property. They just find the two nodes. So ultimately, these two codes are going to set first and second as two nodes which are violating the BST property, and swapping which will make the BST correct. So we just need to find the two nodes, swapping which will make the BST correct. That's what these codes are doing. And after running these codes, we can simply swap the data of first and second, right? So the purpose is to only find first and second. What are we doing in these two codes? We are simply doing an in-order traversal. While doing an in-order traversal, if we see a violation, we follow the same array-based approach. If first is set null, then we set the first as previous, and we always set second as the current node, right? Since it has to be an in-order traversal, we need to traverse left subtree first, then we need to check for the current node, and then we call for the right subtree. When you are doing in-order traversal, your previous pointer or reference might be null. It will be null for the first node that you visit in the traversal, right? Because we have initialized previous as null. Let's do a dry run of this code on this example tree. So we initialize previous as null, right? Now what we do an in-order traversal, which means we are going to begin from here, then we are going to come here, we are going to come here, and then we are going to go to the left of it. We end up with the base case, root is null, so we return. Now we come to 4 and we have the previous as null. So we will not be checking for this condition here in this code or this condition in this code, because previous is null, right? So we will not check for the first node. So this code is done for this particular node. Now we come to 60. The control goes back to the parent. Before sending control back to the parent, you set the previous as reference or address of 4, right? So when the control comes to 60, you check whether it is greater than previous or not, right? That's what you do in this code, because this time previous is not null. So it's greater, you are fine. So you will update the previous as 60. Now you will come to 18 and this time you will see a violation. So what you will do, you will set the first as previous 60 and you will set the second as current node, which is 18. Right? Now you will again continue in auto traversal. When you are doing in auto traversal, next node that you will visit is 8. And before visiting 8, you will set the previous as 18, right? The node that you visited before 8. When you come to 8, you will again see a violation. This time what you will do, you will check that first is not null, right? So you will keep the first as 60. You will only update second as, so this time you will update second as 8, right? You will update the second as 8. And then you will again continue the in-order traversal. You will come to 20. You will not go inside this if condition because it's not violating. Then you will come to 80. You will not go inside this if condition because this is also not violating. 80 is greater than the previous. So ultimately your first points to 60 and your second points to 8. So you, after running this code, you have correct first and second. And after running the code, you simply need to change the data at first and second. You have reference or pointer to them, right? So I've written here equal to, that means they are references or pointers to these values. And we found the correct node, we can fix the BST. What is the time complexity of this approach? This approach simply does an in-order traversal, so it's big O of n time.